Good afternoon, everyone. So this is week 2. So the number of attendants comes too low now. From next week I will see who are the people attending, or even I can see now who are the people attending. The important thing is we expect all students attend the classes, either at least through Zoom or something. Okay? And I also noticed not many students watch the recordings. So let's see how that goes. And also the team selection. Many students not selected the team, so I randomly allocate them. So we have altogether 21 students, 18 in Melbourne, 3 in Rockhampton. So we have odd numbers, so one group ended up with 3 members. So I put, since Rockhampton had 3 students, I put them together. Okay, all other groups have 2 members. And the team project details are given. And the classes, as you know, it's not online, you need to be on campus. So you should know what are things we are discussing, right? So the exam is not easy if you don't attend the class or if you don't work out by yourselves. If you rely on someone else, you can find out. Okay, so let's start. I think you are almost adults, so I don't want to explain too much. So you should know. And remember, it's not a magic to learn everything overnight. Okay, so it won't happen. Okay, so let's start. So last week we talked about how to find out loads, or where to find out loads, dead loads and live loads. And we also discussed about the structural design process and the load combinations and everything. So technically you should know what are the loads acting on the structural member. So you should be able to find what are the loads. In this unit we are mainly focusing on dead load and live loads. Okay, so you should be able to find out what is the dead loads and live loads on the structure. And today we will look at the design process. So before we go into the design process, we need to know a little bit about the basics of concrete properties and the basics of the design of RC. Beam or slab or column sort of. Okay. So concrete, as we discussed briefly last week, is a mixture of cement, aggregates and water. So generally the aggregates give the strength, the cement is used as a binding agent. Okay. So So we need to make sure we have a correct mixed proportion to get the appropriate strength. In addition to the concrete mix design, you also should know, or we should follow the correct procedure for the concrete placement. It includes foam works and vibrations. The curing also important. So that's especially the early stage of the concrete strength is determined or affected by the curing. Sorry, the proper curing is the key things. So that's about the concrete. We discussed briefly these things last week. So the properties in terms of the strength, concrete have good compressive strength, but quite brittle. What do you mean by brittle? The failure will occur suddenly, okay, like clay or ceramic, okay. So it's a very brittle, so there is no much plastic behavior after yielding. It's sudden failure, so that we may not have enough warning for concrete failures. Okay. And also the tensile strength is very low. So what we do is we provide reinforcements in the tensile zone, or sometimes we also put pre-stressed bars. We'll talk about the pre-stressed design from week 6 or 7 later. So the strength wise, good in compression, weak in tension, but very brittle. So durability, generally concrete have good durability. It's doesn't affect much with the corrosion or other things, but there is some issues with these improper placements, so that cause some internal cracks and voids, so that also cause some other issues, something freeze down issues of the cracks due to that water goes into the voids and freeze when the temperature goes down, so that make the cracks and others. So, but durability wise, compared to other materials, concrete relatively have good durability. Okay. Fire resistance generally good up to about 300 degree. After that, strength will reduce significantly. At 300 is good temperature for day-to-day life. We never reach that one. In the case of fire, 300 degree, that's quite low, so we need to do some precautions for that. So the fire resistance relatively good. It won't melt as soon as it reaches 100 or 200 degree. So the cracking failure or failure mechanism normally happen into 4 stages. So the first one is a micro cracks will develop, so that we may not see those cracks. Okay. So it can happen during excessive loadings or improper curings, or due to other reasons. Something like a corrosion of the steel might micro crackings. So generally the micro cracks is the one start in concrete. So then that will expand further, and when the micro cracks expand, then we should be able to see the cracks in the concrete mortar. So small cracks, visible cracks, may not be a serious issue sometimes, but when it is connect those cracks one to other, then that will cause further propagation of the cracks and failure of the member. So the failure mechanism developed into 4 stages. The compressive strength of the concrete affected by many factors, but these are the main factors. Concrete mix is the one. As we discussed, the proper concrete mix is important. The admixtures, there are lots of admixtures we use for different purposes, so that also will affect the strength. The curing type, how you do the curings, whether it's a water curings or straight curings. So we should look at those things and how long we do the curing. The last one is age. As all any other materials, as time goes, strength will reduce. Okay. So the strength of the concrete affected by many factors, but these are main things. Tensile one, it's quite weak. As we discussed, it's maximum about 10%. Okay, but it varies between 8 to 15, but typical number is 10%. And the failure is Van der Waals force, the failure of the Van der Waals connections between these molecules. Okay. So it's quite Van der Waals bonding. The bond strength is very weak, as you know from chemistry. So that's gives a poor tensile strength. So these are general idea. So where to get this one? So you know AS3600, the clause 3.1 gives the concrete properties. Okay, so everyone should have the access of AS3600. Last week I explained how to access AS3600. So clause 3.1 gives all the properties we need for the concrete design. So you should be able to read the clause 3.1 and able to find out what is F-C means, and for given F-C, the characteristic strength, what is the modulus of elasticity, and the density we have to find. Everything is given there. And also the clause 3.2 gives the steel properties. So normally we use N-type bars, normal ductility bars, so that have 500 MPa strength. And we may also come across R-type for shear strength, shear reinforcements. It's a plain bar, there's no ribs, but the reinforcement normally have ribs. Okay, you should know that one. So in Australia we have N-type bars, normally started to use or come into the market from 2000, early 2000s. But if you come across any old concrete structures, if you come across any old concrete structures only built in 90s or earlier than that, you might see the reinforcement bars are noted as Y type. Y. So Y type bars have the yield strength of 400 MPa. Right? We don't use that one now, but if you come across those bars in the old structures, that is 400 MPa. The modulus of plasticity for the steel is given as a 200. Okay. As you know, that's variation, but for the design purpose we use 200. So these are the properties, and you should know where to get these ones. Okay, so as we know, all our design, okay, so we know that the design according to the limit state principle, so we use ultimate limit state and serviceability limit state, but they also need to have proper fire resistance, and it should have good durability. So the durability requirements are explained in section 4 of AS 3600, and fire resistance are explained in section 5. Okay, so the durability section, they are mostly focus on 3 criteria. So what that means, our concrete structure should service to the client. Okay, so that means it should be able to carry the required loads, the service loads. Okay, not ultimate, I'm talking about the service loads, this is normal loads. And also that should be able to say in the particular environment that is exposed to. Say the buildings in seaside or coastal environment is quite different from something inland buildings. Okay, because the coastal side have quite risky or exposed to the salty wind or breeze, so that will make the steel corrosion faster than other places. So we can't put the same design for inland structures, something 100 or 200 kilometers from the coastal to the coastal region. So we need to look at those things carefully. So the environment is another important aspect. Okay, the first one is our service loads, how the load comes from, and the other one is the environment. Other one also the time. So I think I touched a little bit last week. So the design life of the structure. So AS3600 assumed a design life for 50 years. Okay. The steel standard AS4100 also assumed 50 years of design life. The bridge design normally assumed as 100 years. Residential houses 25 years. This is normal assumption of the standards. So based on that, the durability criteria also will change. So keeping these three criteria to save our structure or to have good durability or required durability of the structure, we use the section 4. I quickly open the section 4. Give me 1 minute. So this is the Australian standards. So if you don't know any notations in the standard, you should go to the section 1.7. It's explain all the notations used in the standards. Okay, so if you're not sure anything or what is this one, so you should refer. So quite large list. Okay, so if you go to the section 4, the section 3 is the properties of concrete I explained earlier. This is properties of reinforcement, and we need this section for pre-stressed concrete. We will talk about that one later. So this is the durability things. So they explain all the things here. Please have a read. Okay. So here they give some exposure classification. So based on the environment, they have some classification. Okay. So if it is something on the seaside or structures on the ground, because when the structure is touching the normal soil, so then we should be careful, because it's depend on the acidity of the soil and the moisture that will give some issues to the reinforcement as well as concrete strength. Okay, so all these classifications are explained. Okay. So you can see the members touching the soil. It's depend on the soil type. Okay, so they give the classification. So if you know the classification and the usage, okay, that's other things. The 3 criteria I mentioned: service load or serviceability. Should be able to service to the client. That means the member should be able to carry, or it should be able to use for the purpose, and also it should consider environmental. So the environmental things comes under the classification of the exposed condition. In this one also they give the climate zone. Okay, so they talk about tropical or temperature things. So once you have this one, they talk about the concrete. Okay, for each different classification, what type of concrete we need. And you see this minimum strength of the concrete for each exposure classification. Okay, and also the curing and other things. But you can see as we go severe exposure classification, we need a higher strength. Okay, so that's one thing based on the exposure classification. Also, it depends on the usage. If it is subjected to some traffic loadings, traffic means the moving load. It doesn't mean always vehicles. Okay, so if it is a footpath, okay, or driveways. Okay, similarly in the shopping centers, the normal area. So they talk about what is the minimum strength based on those requirements. So we need to look at the exposure classification as well as the traffic of the loading. So based on that, we should be able to find out what is the minimum concrete strength we require for our design. So we should look at all the conditions. So once you have, then we also talk about the freeze and thawing condition. So that means if the temperature goes below 0 and very often, so then we should be able to look at that condition as well. So if your structure in a place where the temperature will go below 0 and come up, like say in Canada sometimes, or some places where the temperature goes or drop below 0 in the night, and the daytime it's increased above 0. So what happened if you have cracks? Some water might go in, and when it is freeze, the water volume will increase when it's freeze, especially around 4 degrees, the volume will increase. So there's a sudden change of volume in water. So in that case, we need to look at those conditions as well. So please read this section. Okay, so what are the conditions they are talking? We may not use each and everything in our assignment, but we should look at those things. Okay. This is sulfate soil for the aggressive soil kind of things. So once you have this concrete strengths for the given condition, the next one is a cover. Cover means the distance from the bottom part of the concrete to the nearest reinforcement. So that is something. Give me a second. So when you have so if you have a structure, a beam or something, cross section is like this. Okay. So you may have reinforcement. It can be some shear reinforcements. So if you have shear reinforcement, and then you can put the reinforcement here. So the cover is the bottom part of the extreme steel to the nearest concrete surface. This is cover. Cover is defined. So if you have only reinforcements, if you have only longitudinal reinforcement, no shear reinforcement, so you might put the bars like this. So the cover is the extreme location to the nearest concrete surface. So this is cover. So we need proper cover because the other, say, chlorine or any other acidity things might penetrate into the concrete. So we can't stop it. Okay? We can't stop, but we can prevent, or we can make it to delay. Okay, so we put enough cover. It will take a lots of long time to reach to the steel, so the steel will be protected. Okay, so that is cover. So if you look at the table, they give the minimum cover. You also don't want to have very large cover, because if you have large cover, technically this part of the concrete, okay, will not take any loads. It will not carry any loads, or it will not increase your bending or shear capacity. Technical. Okay, little bit, but not bending capacity at all. Little bit shear capacity, but it will not help much. So if you put too much cover, then we are putting too many concrete without much usage. Okay, so that means it will increase the dead load. So if you increase the dead load, what will happen? You will end up with a large bending. So again, you need large sections. So to avoid that one, we tried to put it to the minimum cover. So this standard says what is the minimum cover for each exposure classification. So you can see if it is A1, we may able to use 20 MPa concrete. For A2, 20 MPa concrete is not recommended. Okay, so even if you use it, the cover will be more than double. So we don't move that one. So this one, the line shows what is the recommended strength of the cover. Sorry, strength of the concrete. So if you have this one, so that means for B1, we don't want to have 25 MPa, so we want to have it 32.
Here is 60 millimeter.
Yeah, 60 is there, but it is not very recommended.
Oh.
Okay, you can see it's almost double the cover.
Oh.
So it is not recommended, but if you still want to use it, so you need to provide quite large cover.
Yeah.
Okay, so you can see the increase below that line, say from here to here 5 mil, 15, here is a 25. Okay,
Yeah.
So quite significant increase. So if you say, for example, if it is a C2, you should have more than 50 MPa concrete. Okay. So that is the required cover for the exposure condition. Okay. So the section 4 will give what is a minimum cover and what is a minimum strength of the concrete based on the environment and the usage of the structure. So that's section 4. Please go and read that one. The next one is a fire resistance. As I told, the fire resistance also important. In case of fire, we should have enough time. The fire brigade or anyone to react to the fire emergency. So that means we should allow sufficient time to evacuate the people in the structure. Okay. So the fire resistance, we are considering 3 different things: resistance or adequacy, structural adequacy, integrity, and insulation. Okay. So there are 3 things. If you have fire in the building, so there are 3 important aspects. So the first one is the insulation. Okay. So the area, so if you have a fire here, so your structure should prevent the adjacent area. Okay, so that means, so let's say you have fire in this room. So we should make sure you should have enough insulation so that fire or temperature will not exceed outside this area. So that means the next room or the other surroundings rooms will not get the fire, or the temperature should not exceed more than 140 degrees. Okay, for at least given time. So if you have fire here, adjacent build areas, rooms or area should be protected so that the temperature will not reach there more than 140 degrees for at least sometimes. So that is the first things. So normally the FRP, the fire resistant periods, are given in 3 different numbers. So in this slides I put 120, 90, 60. So normally they give 120/90/60. So it can be 3 different numbers. So the last number talk about insulation. So here 60. So that means 60 minutes at least. For 60 minutes, the adjacent area should not get the temperature more than 140 degrees due to the fire. So that's the first thing. So that means your area should be insulated using proper concrete so that it will not go to the adjacent area. So the next one is integrating. So you should get any smoke or flame into the adjacent areas for 90 minutes at least. Okay, according to this one. So it doesn't mean always 90 degrees. So according to this FRP, so you should have enough time so that, because if the smoke comes, sometimes it's difficult to move. So we should make sure the smoke will not come out of the area at least for 90 minutes. The last one is the adequacy, structural adequacy. So structure should save, so that should not collapse for 120 minutes. Okay, so those are the three different things. So we need to make sure we are satisfying all three conditions. So how to satisfy these things? So we should look at the standards. So the BCA code, Building Code of Australia, will tell what is a minimum FRP, fire resistant period, for different structures. It's depend on the usage, whether it's a commercial building or public building or normal houses or normal apartments. So the BCA will give minimum requirements. So if you should have access for the BCA code through the library website, you should be able to look at. But if you have that one, you should be able to explain what is these three numbers means. Okay, so if you have those things, we should go to the section 5 of the AS 3600. So the section 5, here they talk about the average axis distance. So here you can see some diagrams. So there's simply, if you have a structure, the reinforcements are there. So the axial axis distance is this one. Okay. So for each bars you need to add and take the average. That's what they said in the standards here. If you have multiple things, area of the each bars and the distance. Okay, area of each bars times distance, you need to add for each bars and divide by total area, and you will get average axial distance. But if normally we don't put the different areas, so normally we'll have same areas. So if everything in the same distance, so this is axial distance. If you have two layers, so the axial distance will be like this. Okay, so these are the axial distance. It's not very complicated. The standard covers every different possibilities, so they give a complicated equation sometimes. So this is the axial distance. So the standard, look at this one, and depend on the so for the adequacy, 2 is supported slabs. So for all different type of structure members, they talk about what is the minimum axial distance. So for slabs, beams and everything they gave. So this is for beams. So in this section they explain what is the minimum requirement for the axial distance and others. Similarly for slabs and everything. So you should be able to read this section. It's not too complicated. So if you go to that one, so minimum dimensions are here. Okay, for FRP adequacy time. So if it is 120, these are the minimum dimensions. So you should be able to look at those tables and get the minimum axial distance and the dimensions for the beams. Okay, so you should check these things. So these two things comes before any design. So we need, before we start anything, we should make sure our structural members are satisfying these two things, durability and the fire resistance. Okay, so then only we will do the design. Any questions? Any questions? All good. So there's two things for the project, and we'll talk about that one in a minute. So once you have those things, durability and fire resistance, we need to start the design. So let's start with the design, with the beam design. Beam design and slab designs are quite similar. It will be different, but the fundamentally similar approach. So we will start with the beam design, then we will go into the slabs, then last one is the columns. So we are going to design a beam. So you have a beam, let's say you have a beam, and you know the loads. You know how much dead loads, how much live load on the structure. Okay, so you should know, or you should be able to calculate how much dead loads, how much live load acting on the beam. Okay, so now we want to check whether our beam is good enough to carry those loads. That's all. So what are the checks? So we discussed this one last week. We need to look at two different limit states: serviceable limit state and ultimate limit state. Normally, to check the dimension first, okay, because we don't know. So if you ask to design a beam, or if you ask to design a slab, first I discussed this one last week. I think we need to find out dead loads. Yeah, we need to find out dead loads and live loads. Live load can be obtained. Live load can be obtained from table 3.1. But dead loads basically a self-weight of the structure, or it can be any other permanent fixings. But the important thing is the dead load is self-weight. So if you want to calculate the self-weight of the beam, you need the dimension. Yeah? If you don't know the dimension, you can't calculate the dead load. So what we need to do, so to start the design, we need to assume some dimensions. Okay, so we need to assume say 300 millimeter depth or 400 millimeter depth. So we need to assume some dimensions, and then we need to check whether the dimensions are okay. So the problem is, if you assume a depth, let's say you assume 300 mil. So you assume a 300 millimeter beam, and you are starting design, so you put the reinforcement and everything. At the last minute, in the last check, you find the dimensions are too small. We need to increase. Okay, we need to change it. So you already did all the calculations for reinforcement, shear reinforcement, everything. But when you do something last check, you find the dimensions are not enough. So we need to change. So if you increase the dimension, what will happen? The dead load will change. Yeah, dead load will increase. If the dead load increases, what will happen? All your bending moment, shear force will change. So that means whatever you did, say for example you provide reinforcements and everything, need to be rechecked or recalculated. So that is problem, because we don't want to have all the calculation repeat due to the small final check. So we need to know how to guess or how to assume reasonably correct depth. What check actually influence most in the dimension of the beam or dimension of the slab? Which check? So if you look at those things, the dimensions are mostly controlled by the serviceability checks. Dimensions, not the reinforcement. The dimension of the structure is mostly controlled by serviceability limit state. So generally by the deflection check. So we need to do the serviceability limit state or deflection check as a first check. So we assume some depth. Okay, we assume a depth of the beam. Then we do a deflection check to ensure our assumption is reasonable. So if it is passed, then you can proceed to the reinforcement calculation, so that you don't want to repeat the whole calculation again. Okay, so the deflection checks are important. So we will look at the serviceability limit state checks first, and next week we will look at okay. So we will do all the checks for the serviceability, and we will see what are the checks and how to do that. And next week we will talk about the ultimate. Okay. So please understand the beam design is very important, and if you understand the beam design, slab design is easier. Okay. So very similar approach. And AS 3600, the new version 2018, have quite change of fully revised the shear calculation. Shear design has been totally rewritten from the previous one. Previous version is 2009. So 2009 to 2018, we use a different method for the shear design. So from 2018 onwards, we are using completely different shear reinforcement calculation. as per my understanding, there is only one book has been revised, that is the prescribed textbook. All other textbooks are written based on AS3600 2009 version. So the sheer design or worked examples are not relevant to the current versions. Okay, anyone submitted the previous based on the previous ones will not get any marks. Okay, serviceability limit state. So what you mean by the serviceability limit state? So we are doing checks. We are make sure our beam is performs okay under service load. So what are the checks? In concrete, we are checking deflection and cracks. Okay, these are the two main checks for concrete structures. And if it is bridges, we also need to check the vibration. But deflection and cracks comes for all concrete structures. So these are the two checks. So we need to know how to check the deflection and how to check the cracking. Okay. So deflection check and cracking. So when you have a beam, so let's say the beam is, let's assume a simple beam, and if you have loads, it will bend like this. Yeah. So the bottom part is under tension, top part is under compression. Yeah. So when you look at this maximum bending part, we'll have a bending moment. You'll have a bending moment. So according to the stress analysis or strength of material theory, your stress diagram roughly will be there if it is a normal material. Okay, so we'll have larger tensile stress at the bottom fiber. When the tensile stress in the bottom fiber reach to the cracking strength, okay, that is tensile strength. So when it is reached the cracking strength, you will have cracks. You will have the cracks. So what is the cracking strength? What is the cracking strength? The cracking stress or cracking strength is given by this equation, F dash CTF minus sigma CS. The first one, F dash CTF, is the fractural capacity of the concrete, or fractural strength of the concrete. F dash CTF is the fractural strength or fractural capacity of the concrete. So if you remember, you are undergraduate, sometimes you might do the beam test we talked about last week. Flexural strength of the concrete, we use the beam. So when you apply the 4-point loadings, the concrete will crack or fail. So that gives our flexural strength of the concrete, F dash CTF. Okay, so that is the flexural capacity of the concrete, plain concrete. So we know how to measure, but what we do for the design. what we do for the design. So for the design, we'll go to the section 3.1. As I told, all the properties are given in the standard. This is tensile strength. So you can see the flexural one, F dash CTF, this one. Okay, so if you know the F dash C, you should be able to calculate F dash CTF, that flexural capacity, without doing any test. So this is acceptable for the design. So the flexural strength or flexural capacity of the concrete we should be able to get from the standard. So generally that is the case, flexural capacity of the strength, flexural capacity of the material will be the cracking strength. Okay, when the stress reach the flexural strength of the material, it will crack. That is true for most of the materials, but for concrete we need to reduce some stress, because the concrete is subjected to shrinkage stress. What is shrinkage? We discussed this one last week as well. Shrinkage is the shrinkage means the change of length or reduction of the length over the time due to two reasons. One is the chemical reactions, other one is loss of moisture. Okay, so the chemical reactions will happen within first 5 or 6 days. Okay, most of the chemical related shrinkage will happen within first 7 days, and generally will be almost zero after 30 days. Okay, but the other one, the shrinkage due to loss of moisture, that is called drying shrinkage, normally start from 7 days and it will go over the time. Okay, the shrinkage loss or shrinkage will happen over the life of the beam, generally up to at least 30 years. Okay, as time goes, that will increase. So the shrinkage stresses need to be subtracted because concrete have significant loss in the shrinkage, so we just need to reduct that. So how to find out the shrinkage stress? To find out the shrinkage stress, shrinkage stress CS equal to, stress is equal to how much? How to find out stress? Stress is equal to E times strain, isn't it? Stress is equal to elastic modulus times strain. Yeah, that is basic strength of material. This is basic strength of material. Stress is equal to E times strain, isn't it? Yeah. So the shrinkage stress equal to concrete elastic modulus times shrinkage strain. Okay, shrinkage strain. to find out the shrinkage strain, here shrinkage is explained here. So the shrinkage things, as I told, this is the shrinkage strain. The shrinkage strain, cross number 3.1.7. Okay, cross number 3.1.7. So we need to look at that one to find out shrinkage strain. Okay, so so the cracking occurs when the stress equal to the cracking strength. So this one, fractional strength, you can directly read from the standards. Yeah, and this one, the next one, is the shrinkage stress, that is equal to E, the elastic modulus, that can be obtained here. E values are given here. E values, so if you know that F dash C, say 40 MPa concrete, E value is 32,800 megapascal. So the E value can be obtained from here. That's also quite simple. Then we need to know how to find out shrinkage strain. So shrinkage strain is quite lengthy calculation. Okay, shrinkage strain is quite lengthy calculation. We will discuss this one in the tutorial more detail. So the shrinkage strain is equal to the two components, this one and this one. Okay, so this is the one we need, the shrinkage strain. Okay, so this is the one you need, the shrinkage strain. The shrinkage strain is given by two different components. The first one is the shrinkage strain due to chemical chemical effect. So that is called chemical shrinkage. The other one is due to the loss of moisture, that is called drying shrinkage. So the two things, one is a chemical shrinkage, other one is a drying shrinkage. As I told, the chemical shrinkage generally very dominant in first 7 days. After that it will reduce. Generally after 30 days it becomes very small. But the drying shrinkage will start from day 0, but it will increase as time goes. Okay, so first few days the drying shrinkage might be not very significant compared to chemical shrinkage, but after that the drying shrinkage become more dominant. So the chemical shrinkage is given by this equation. Okay, so you can see in this equation, the T is in days. After how many days? After 10 days or after 20 days. So as time goes, the shrinkage will increase. Okay? So you should be able to get the shrinkage after 5 days or 10 days, or after, if it is after 1 year, 365. Okay? If it is 10 years, 3650. So T should be in days. Okay, and this one this is the final chemical shrinkage. So this will be the maximum, this will be the last. Okay, so as I told, the shrinkage won't happen in one day. It will happen over the time. So after 7 or 10 days, it will reach almost 99% of the final chemical shrinkage. So this value, if it is less than 50 MPa concrete, we have to use this value, and if it is more than 50 MPa concrete, this one. So you know the F dash E. F dash E is the strength of the concrete. If it is a 40 MPa, F dash E is 40. Okay, so we have to use here. If it is 60 MPa concrete, we have to use this one. So we will find out what is the maximum chemical shrinkage using that one, and then we substitute here. Okay, so then we should be able to find out the chemical shrinkage after given time. That is quite straightforward again. The next one is the drying shrinkage. The drying shrinkage given by drying shrinkage is given by this equation here. K1, K4, okay, and then this is the basic drying shrinkage. This is the basic drying shrinkage. So we have two factors. So K1, we'll look at the figure. The K4 is given here. So it's depend on the environment. So it's a arid environment or interior environment or temperature inland or tropical. So here you should be able to look at that interior environment is something like this classroom. So it's not exposed to the environment. Otherwise, if it is external things, so you should know the Australian map. I think it's given in the section 4. Yeah. So tropical areas, okay, temperature zone, right environment. So you should, so this is for the external exposure. Okay, so depend on the location. If you are talking about something exposed to the exterior environment, then you should look at that one, the locations and everything, and then we should able to use the correct K4 value. it's a quite lengthy calculation sometimes, okay? So you should be able to get 0.7, 0.65 for the interior environment, but if it is other cases, you should look at that one. And the basic shrinkage strain is given by this value, and that value is 800 micro strain. 800, this is 10 to the minus 6, it's a micro, so you should 800 micro strain, and you should be able to get basic shrinkage strain. So K1, K4 times this one, K1, K4 times this one, K1, K4 times this one. So this one is straight away here. It's not too difficult, so everything is there, but you need to calculate one by one, that's all, okay? So it's when you do this calculation for your project, please use Excel, because these are very small numbers, okay? If you round it, sometimes it won't give much variations, okay? So please use the Excel so that it will keep all the decimals, so at the end you just round it, okay? So you should be able to find out the drying shrinkage K1, K4 times this one. So K4 is depend on the exposure things, then K1 is here. So K1 is here, this table is here, otherwise you can use this equation, whatever you like, okay? The K1 equation is given, alpha 1 times T to the power 0.8 divided by T to the power 0.8 plus 0.15 TH, okay? So the alpha 1 is here. So we have a new terms. T is the time, you know that, but we have a new term, TH, okay? TH is a new term. I'll come to that one in a minute. So if you look at this one, let's say you know the TH, so you should be able to find out after 10 days or 30 days or 100 days, 1 year, 3 years, 10 years, 30 years. So you should be able to read the graph. So if you know the TH is 400, after 1 year it is around 0.61 or 0.62, yeah, somewhere here. So if you need the very exact number, you can use this table. So now we have a new term called TH. What is TH? So if you are not sure what we have to do, if you don't know what is that, always go to the section section 1.7. Go to the 1.7. If you don't know, just go to the 1.7. So TH T down, isn't it? Small. Yes. Hypothetical thickness. Okay. So how to do the calculation? That is given 2Ag upon UE. So again you have to use what is UE. So if you read that the UE in the bottom, what we will do is, so this is your, say this is the beam. So let's say you have designed a beam. It is a part of the slab. let's say you are designing this beam, okay? So the beam technically like this. Yeah. So we are designing this one. This is a part of the slab, and top of the slab you might put some tiles or carpet. You might put some carpet or tiles. Yeah. So if you have something like that, this face of the beam does not expose to the environment. Okay. So TH 2Ag upon UE, this is the perimeter, exposure perimeter. So if this case, if it is not exposure to the environment, so we need to consider, and this also not exposure. So only in this one, only this part is exposed to the environment. Yeah. So from here, so this is UE, exposure perimeter, not the perimeter of the beam, which section of the beam is exposed to the environment. Okay. So here this part is not exposed, and if you have tiles, if you don't have tiles, yes, this part also exposed. If you don't have any tiles here, this part also exposed. Okay. So only this part is not exposed, so you need to redact that part. It is clear? So the UE is the exposure perimeter. AG is the gross area. AG is the gross area. UE is the exposure perimeter, so that you should be able to find out the hypothetical thickness, TH. Yeah. So if you know the TH, you should be able to read the graph, or you can use the equation. You can use the graph, or this equation. You know the TH, you know the time is from 0 to 30 years or whatever. Okay, so in days, everything should be in days. You should put it, and you should be able to get the K1 value. So you know the K1, K4, and the basic drying shrinkage. So you should be able to find out the drying shrinkage strain. So once you know that drying shrinkage strain and the chemical shrinkage strain, you should be able to find out total shrinkage strain. If you know the total shrinkage strain, you should be able to find out shrinkage stress. So that is the one we need here. Okay. So how to use that one and where to use that one, we will discuss that one in the tutorial class. Today we will talk about some terminology and how to calculate. Okay. So the cracking stress is equal to fractional capacity minus shrinkage stress. Okay. So we'll use that one. We'll discuss, we have to use that one later. So when I say that you need to calculate the cracking stress, you should know how to get that. Okay. So now we'll talk about the properties. So under the serviceability limit state, we are considering service loads. Okay, we are considering service load. So in this case, okay, remember we are talking about serviceability limit state, not ultimate, that is next week. So this assumption will not work next week. This week, okay. So for serviceability, for deflection and crackings, we may be able to use this assumption. So that means the section behave as elastic material. What is a good things with the elastic behavior? We should be able to use all our theories we study in the standard material. Hooke's law, yeah, and everything can be used. So that the stress proportion to strain, okay, everything we should be able to consider, because under the service load, the strain in the concrete members are very small. Okay, in the ultimate is different. The ultimate strains are very large, so we can't use this assumption. So here we can say our concrete structure behave as elastic material. So what is the elastic? Still someone is joining. Okay, we have another 20 minutes class. Anyway, sorry, there may be some noise, so thunderstorm here. Anyway, so that's what some background noise comes. Okay, so elastic. So if you have elastic material, we should be able to use elastic transform section. So have you studied the modular ratio things when you have two different materials? So if you have two different materials, the strength of material you might study. So this is, let's say this is one material, copper. Let's say this is aluminium. So to analyze this one, so we transform one into other. Okay, so generally the copper have larger E value. Okay, so if you want to transfer the whole materials into copper, so the copper will stay as it is, and the aluminium we need only a little bit less, so we transform the area like this. We study that one. So this will be, so if it is a B, this one is B times something like this. Okay, so this is only work for elastic materials. So we should be able to use the same things because we assume under the service load our concrete member will behave elastic. So it has elastic behavior. So I should be able to use this one because our concrete structure a concrete member is a composite material. We have steel and concrete. We have two things. So we are going to use this transform section. So in this case, we have two different cases. One is uncracked section, another one is a cracked section. Okay, both are elastic material, remember. So uncracked section, so this one, so look at this one carefully. This is strengthened material, okay, but you study in your undergraduate. So this is the section. Section is B width. Overall depth is capital D. This is effective depth. Small d is the effective depth that measured from the compression side to the centroid of the reinforcement. Centroid of the reinforcement. That is called effective depth. Small d. Capital D is the overall depth. So that is our section. So it is a little bit difficult because steel and concrete, very difficult for us to analyze. There's two different materials. Okay, so what we do is we will replace the steel with the concrete. Okay, we replace the steel with the concrete. So which one is stronger, steel or concrete? Steel is stronger. Yeah, steel is stronger. Steel can take large stress, isn't it? The E value is higher. Okay, for E value, elastic modulus is larger for steel. Steel have 200 gigapascal. Concrete is around 30 to 40 gigapascal. So almost 5 times of the concrete one. So when we replace the steel with the concrete, I need, say, let's say, for example, okay, this is 200, doesn't change. It can change, okay, can change. So for example, I just take 32 gigapascal, okay, for example. So if we replace the steel with the concrete, we need more concrete. Okay, so how much? ES upon EC, 200 upon 32. Okay, so if you keep the calculation, 32
6.25.
6.25.
6.25.
25.
Yeah.
Okay, so that means almost 6 times, 6.25 times, 6.25 times of the concrete. Okay, so that means, remember, look at this one carefully. You need to understand. So we have steel. Okay, I'm going to replace this steel in the same location. Same location. So if it is, for example, if the area, 3 areas, say let's say 60 millimeter square, okay, all 3, 60 millimeter square. So if I replace this concrete with the, sorry, if I replace this steel with the concrete, I need 60 times 6.25, this one. Okay, this much I'm replacing the steel with the concrete, so I need this much of addition, okay, because steel have larger E value. So how much it will, can you just quickly, sorry.
375.
Okay. So I need 375 square millimeter of concrete to replace the steel, the equivalent thing, okay? Equivalent thing. So I need 375 millimeter of the concrete. I'm going to put here. So I am going to remove the steel and put this much of concrete. Okay. So if I remove this steel, what will happen? There will be some 3 holes. Yeah, 3 holes, because I took the steel out and then put the concrete. So out of this 375, 60 will replace here. Yeah, 60 will go there. So you have 315. We need to put somewhere, but they should be in the same line. So I need to put it here outside. So this one, this area, the shaded area is 315. Okay. You remember? Sorry, you understand? So a little bit difficult, sometimes a little bit trickier one. So first I calculate how much equal concrete. So this is N times, N is the ratio of the E value. So this is N time of the area. N times of the area. Okay. So one part of that will fill the holes. The rest will come as a additional attachment here. Yeah. So that is what I put it here. So N time AST I need here, but 1 will fill these holes. So we'll have N minus 1. N minus 1. Okay. Why it is minus 1? One part of AST will fill the holes. Okay. I need total of N times of the area of steel to replace by concrete. Yeah. So now I need to consider this section. This section. This is strength of material. Okay. So this section, I need to consider this section. So this is, the whole section is made of concrete. The whole section is made of concrete. Yeah. The whole section is made of concrete. It is not a symmetric section because here we have more area. So our centroid will be somewhere here, not in the middle. If it is a rectangular one, it's in the middle, but it is not rectangle. It's a little bit odd shape. So our neutral axis or the centroid will be here. So I put the centroid distance. I put the centroid distance as a y bar. I put the centroid distance as a y bar. Okay, centroid distance as a y bar. So that means above this one, and below we should have same moment. Yes, centroid means equivalent, isn't it? So we'll take the moment about this line, so this area times that centroid, and this area by the centroid, you will get that one, and if you solve you will find out the centroid distance. Okay, and then if you use the second moment of area, you should be able to write the I value like this. I is the second moment of area for the equivalent section. So in the tomorrow's tutorial class I will work out. So you will find the transform section, the uncracked section is like that. I will explain a little bit more in detail about how to get the I value, because I don't think today we have enough time. It will shut down in 2 minutes, less than 5 minutes. Okay, so tomorrow's tutorial we will work out with the numbers, so you will understand. But what we need to understand, when you transform the composite materials, composite section into one, the equivalent area is n times of the area. So we just replace it. So the one part, the minus one, you should understand why they put the minus one. The one is fill the holes. Okay, because it's uncracked section. The next one is a cracked section. So cracked section means the concrete has cracked. Okay, so if you have cracked section, so let's say this is the, below this one everything is cracked. The neutral axis means below that's tension, above compression. Okay, so it's cracked here, so there is no concrete because concrete is cracked. So I'm going to replace the steel with the concrete. Whatever the concrete here is already cracked, but I just, for the analysis, I am replacing this steel with the concrete. As I told, this is n times of the AST, no minus 1, because there is no holes, there is no concrete at all. Okay, we don't need to fill that holes because there is no concrete. It's only steel in that part. Okay, there is only steel below the neutral axis because concrete is cracked. So there is no concrete below the neutral axis, so I don't need to fill that holes because it's already only steel. So this is n times of the AST. So if you understand these two, okay, we should be able to, I will explain in the next class. I will continue this one. Okay, next class tomorrow, and then we will talk about deflection calculation. Okay, so if you have these two clear, and rest of the part is easier. So before we close, and only we have 2 minutes, the project is already there. Okay, project is already there, team project task. Tomorrow 5 to 6, isn't it? 5 to 6, we will talk about the project requirement. Okay, the team is already there. I already put you in team if you don't select the team. So please look at that one. I gave until yesterday. Those who don't select, you should accept whatever there. I can't do anything better. I let you select, but if you don't do that, okay. So tomorrow 2 to 4 is a tutorial class. We will discuss, continue this one and work out the tutorial, and then 5 to 6 we'll talk about the project. please attend. I will explain what you need to do.
Yeah.
Okay?
Hello.
Yeah.
Sir, is there any chance that we can combine the team? Like, I don't know that. So we can do the group of 3 instead of 2, if there any chance.
No chance. I put 2.
Okay, now you put the Rockhampton 3, so I'm just
Yeah,
asking
because
whether
we have odd numbers.
Okay.
One team end up with 21 students. One group will end up with 3. We can't avoid that one.
Sir,
Okay.
can we change the team?
Sorry?
Can we change the?
That's what I let you select the team until yesterday. You haven't select. Isn't it? I asked
Sir,
you to select until it's open until yesterday night.
Yeah, sir, but we don't know. Can we, because me and Kalrav are living together, so can we make a group of 2? So easy to make project because we are living in the same house.
So you should select that one.